previous up gives an introduction to basic ideas behind PCA, such as latent variables, principal components, variances, distances, and so on. And if you try this app, you remember there was a button fit that fits the orientation latent variable to capture the biggest spread of the data, right? So it makes the automatic, it finds the orientation of this latent variable automatically. How it works? There are several algorithms to find this orientation. One of them is called NIPALS. It's not the mostly used algorithms, but one of the simplest one also that gives you an insight how principal component analysis works. So let me use NIPALS to explain this idea of finding the best orientation of latent variable to capture the biggest spread of the data. Well, you can see that my initial orientation is this one. So initially, latent variable has the same direction as x2, right? And then you can also see it here. So this is x1, this is x2, this is just the coordinates of the blue points. And then if you look at the scores, you remember scores, it's a position of the projected points along this line. You can see the scores and the x2 coordinates are identical because now the principal component 1, it's the same as x2. Right? You can also see it here. So this is orientation. This is a loading vector. You remember loading vector, it's a unit vector that starts in the origin and it's oriented along the direction, right? So you can see it's 0, 1. So 0, it's x1 component, 1, it's x2 component. So we can see that our current loading vector oriented exactly along the same direction as x2. Now, how to find the orientation, the correct orientation? Apparently, the orientation is not good. Our orientation should be maybe like this. The idea of NIPALS is following. If we want direction of the biggest spread of the data, we need to utilize covariance between the variables, right? And what we can do, we can first of all take the scores, the current scores, and then we can compute covariance between every variable and the score vector. So first we compute covariance between x1 and t. And since the data is mean-centered, you remember what is covariance? Covariance is when you find how far this point is from the average of x1, and then you find how far this point is from the average of t, and then you multiply these two distances, and then you take a sum of these multiplications of this product, and then divide to n-1 to find the covariance. But in this case, the average of x1 and average of t are zeros because we mean-center the data. So in order to find the covariance between x1 and t, we simply multiply this value to this value, and this is exactly the product of these two values, right? We do it for every point, and then we take a sum. So if I want to compute covariance, I strictly speaking need to divide to n-1, but in this case, for the sake of simplicity, I will divide it to 10. It doesn't change anything because I divide to the same number. So it's simplified or biased version of covariance. So this is covariance between x1 and t if I take this sum of these products and divide to 10. So this is exactly what you see here, right? So I take this and I divide to 10, and then you can say I round to 3 decimals. So this is my new value. So this is covariance between x1 and t and 0.156. Then I find covariance between x2 and t, right? And the same idea, both variables are mean-centered, so I just need to multiply these two values together and then take a sum and divide to 10. So this is covariance between x2 and t. Strictly speaking, it's a variance of x2 because you remember t at the 0 iteration is the same as xt. And now my next iteration, orientation of loading vector in the next iteration will be simply these two covariance values. So I take this covariance between x1 and t and take it as a portion of p1, the loading vector for the next iteration along x1, and this is the portion along x2. However, you remember that it should be a unit vector, so length of this vector should be equal to 1. If I compute length of this vector, and it's Euclidean length, you take a sum of these two squared values and take a square root of the sum, it will be 0.22. So you can see it's almost 5 times smaller. What I can do, I can take this value and divide to length. I take this value and divide to this length. And in this case, I will make sure that the length of the new vector will be equal to 1. And that's what I do here. It's called normalization to unit length. So I take 0.156 divided to 0.22. It gives me 0.826. I take 0.106 divided to 0.22. This gives me 0.564. And if I compute length of this vector, you can see it's equal to 1. So that will be orientation of next orientation, or orientation of loading vector, orientation of principal component. In the next step, when I click 1 here, I will use this one, this vector. Then you can see now it's not 0 and 1 anymore. Moreover, x1 will have a bigger influence on the orientation comparing to x2, right? Let's see how it looks like. So let me take this first step. And then you can see, indeed, we already almost match the correct orientation, right? You can see these two values. It's exactly what we calculated in the previous steps. I will just go back. You can see this is our calculations on the step 0, and this is the new loading vector. And then we simply repeat this procedure. So now we have new scores, right? So now we project all these points to this new loading vector, so to the new orientation of principal component. We got new scores values. Now we compute covariance between x1 and t, new covariance, this one. This is sum. To get the covariance, we need to divide to 10, so this is the covariance, you can see. Then we do the same for x2 and a new scores t, so this is the products, sum, and this is the covariance. Then we say, okay, in the next iteration, the coordinates of the loading vector will be the following. It's a covariance between x1 and t, and covariance between x2 and t using the current orientation, right? Again, we compute the length of this vector. We found that the length is 0.5. It's too small. We need to normalize it to unit length simply by taking this coordinate, and then divide to this length. Then we take this coordinate and then divide to this length. We will get these two values. And if we take this vector, the length will be equal to 1. And now you can see interesting thing that the current coordinate and the next coordinate for x1, it's almost the same. It's very small difference. You can see here we have 8,3 and here we have 8,9, right? Similar here. So the current coordinate, this one, and the new coordinate, this one, also very similar. So it means that the next step will introduce a very small change. And you can see it here. If I click 2, you can see, it's rotated a little bit, but you can see the rotation is much smaller comparing to rotation between 0 and 1, right? And then we repeat this procedure again. So we got new scores, we got the new projections, got new scores, compute new covariances, and so on and so forth. Now you can see that the difference is even smaller. So here we have 0.890. Here we have 0.893. So you can see the difference in the third decimal period, right? Here you have 457, here you have 459. It's also quite small difference. So you can see that third step introduces very tiny change in the orientation, right? And then if you take step number 4, you can see there you cannot see the difference anymore because the number of decimals is limited. Of course, there is a difference, but this difference is much further away. It's even smaller. And then if you take 3 or 4, visually, you do not see it. You do not see any rotation between 3, 4, and 5, right? Also, there is a small change. For example, you can notice it here. If I have 3, this sum of these products is 1.870, but if I use 4, it will be 1.869, very tiny difference. But for between 4 and 5, you cannot see it even here. Okay. And then you can also see that, for example, the explained variance, the percentage of explained variance for last 3 points, you can see it's still the same, right? It's 9,368. For 2, it's a bit smaller, right? So it's 67 instead of 68. Again, very tiny difference. But between 3, 4, and 5, you do not see any difference. Okay. So that's the basic idea of NIPALS. So you compute orientation of loading vector simply by taking covariance values between every variable and the score computed for the current orientation.